So today we're going to look at the connection between calculus and finding the length of a curve. And just to set the stage, we've been kind of seeing thus far that when we work with straight lines, those are easy to do. And we don't need calculus to calculate things with straight lines. Like if I wanted the area of this figure here, I could partition it into a bunch of little rectangles and find the areas by doing the base times the height. Same thing with volume in 3 dimensions. Even though it looks like a bunch of triangles, it's still made up of only a bunch of straight lines. And it's easy for us to see that 2 triangles make a rectangle. So with volume, we can just find the area of that base, which is again pretty much just rectangles, and multiply it by the height. But when it comes to curves, with curves we need calculus. So for example, we can borrow some ideas from straight lines. Like if I wanted the area under the curve, I could just go ahead and use a bunch of rectangles. But as we've seen, those rectangles either over or under approximate. And what we need to do is like cram as many rectangles as we can to get the exact area. So we can kind of see some similarities, like each rectangle I draw, the height is defined by the function's output, and its base is defined by whatever arbitrary width on the x-axis I decide to slice it into. And that's where calculus comes in. Because that size of the slice has to approach 0, we're going to need to sum all those teeny slices. So again, it looks similar to 2 dimensions. Or just straight lines, excuse me. But since we have a curve, we need this calculus part. Same thing with volume. We can see some similarities to how we calculate volume with straight lines. We had talked about how we could use something we know, like a disk, and we can see pi times r squared. That's just really the area of the base, and then dx is really representing the height of those disks. So again, with the same argument is, well, how many disks am I supposed to fit in there? Well, infinitely many, which means that arbitrary width is going to get closer to 0, so I need to go ahead and introduce the integral symbol. So extending even further, when we deal with curves, a lot of time integral calculus is very applicable to finding real-life answers or real-world application. So we're going to continue with the idea of curves versus lines in our topic for today. So if I asked us to look at a curve, a natural question in my opinion is, well, how long is that curve? So if we looked at the curve y equals the square root of x on just the interval from 0 to 1. So I have that function here. So here's the square root of x just defined on 0 to 1. Now, I can't find that distance right now because it's not a straight line. So let's just compare it to a straight line for a second. So below that, I'm going to put in y equals x. And on my notes here, that's where I'm going to start. I'm going to put this in, and that purple line is y equals x. Now that is a straight line, which means if I wanted to find that distance, I don't need any calculus, right? So let's call this distance for that line. Now if I wanted to calculate the distance, this is clearly just a Pythagorean theorem, right? If this is the point 0, 0, and this is y equals x on the interval from 0 to 1, that must be 1, 1. So we can see that straight line as a combination of 2 other straight lines, which again, super easy to deal with. This distance is 1, and that distance is 1. So if I wanted to calculate the distance of that hypotenuse, which I've labeled just dis, that distance, if I squared it, I would get leg squared plus leg squared. So if I just wanted that distance alone, I could take the square root of both sides, which is the square root of 2. So I know that from y equals x, or y equals x on 0 to 1, that distance, which I'm now going to erase, that distance is the square root of 2. Now thinking logically, if I started at this point and I wanted to end at that point, the shortest distance between any 2 points is a straight line. So to get from 0, 0 to 1, 1, the shortest distance I could ever travel is the square root of 2. So if we go back and look over at this curve here, which I can also draw on my picture, since that curve is starting at 0, 0 and also going to 1, 1, but it's not taking a straight path, I know that the distance of the curve, so the length of the square root of x on that interval, is greater than the square root of 2, because again, that's the shortest distance it could be. But I don't know anything really more about it at this point, as I just know that it's not a straight line, so it's pretty hard to do. The approximation of the square root of 2 is kind of close, but probably not really that close. But what could we do with that idea is the farther away from that line that this curve gets, the less accurate our approximation with the straight line is. But what we can do is realize that there's a lot of straight lines that we could add up together to make a curve. So on my graph over here, I'm just going to remove y equals x. And I'm going to look at y equals the square root of x, but I'm just going to zoom in at some arbitrary point, just some random part of that curve. Now when I zoom in, That just looks like a straight line. So let's draw that for a second. And I don't know where I am on my coordinate plane, so I'm going to try to be ambiguous about that and just put it floating somewhere in the first quadrant. Just to emphasize, it doesn't really matter what point of the graph I zoomed in on. You don't really know, especially because you don't know where I'm, you can kind of see to begin with. But no matter where I go, I'm going to get a straight line. So I'm just going to draw some arbitrary straight line somewhere in the first quadrant. But if I look at that arbitrary straight line, what I can see here is this little straight line. So this right here, this is one tiny piece of the curve. And it looks like a straight line. So let's estimate how long that is. Now with this, since we don't really know where we are, like in this example here, I knew the left and right distance was 1 and the up and down distance was 1 just because I knew where I started and where I stopped. But these are just any arbitrary points, right? I could zoom in anywhere and the picture looks the same. So I don't know how far left and right I traveled, so I'm just going to call that delta x and call that delta y for the change in x and the change in y. Well, if it's a straight line, that's good, right? That's what we set up here. Straight lines are easy. I don't need calculus for that. So we could calculate that distance. I'm going to call it h at this point, reminiscent of the hypotenuse of this little right triangle I've created. So by the Pythagorean theorem, h squared is the same thing as the change in x squared plus the change in y squared. So if I wanted to just get that h alone, I would just take the square root of both sides. Right? Well, this is the conceptual idea then. I just figured out how long h was. And if there's one tiny piece, I can figure out that distance. Let's just call this h1, because that's just one arbitrary place I zoomed in. So like maybe I found the length of the curve that's on this graph right now. That's h1. Well, I could just pick a different part of the graph and zoom in there, and that's a straight line. So one tiny piece I can calculate. So I'd add another tiny piece plus another tiny piece. Right, so like, in other words, if this was h1, I could calculate that little bit of a straight line there. And then I could calculate the next little bit of a straight line, call that h2. And then calculate the next little bit of the straight line and call that h3. So the idea here that we're starting to see with calculus is I could add up all those tiny straight segments. And what I'd see is all those tiny straight segments, if I put them end to end, would make this curve, because no matter where I zoom in, so I'm going to do, let's pretend I'm going to find h1. Get a better scale here. So if I just zoomed in here, this straight line is h1. So I could just go over here and find this straight line, that's h2. Add it up to this straight line, that's h3. Add it up to this straight line. And again, these all look like straight lines to me. I can calculate straight lines. But when I zoom out from all those tiny little pieces, well, now it's the square root of x again. Right now it's a curve. So that's our calculus idea. So we're going to do a little bit of notation here for a second. The first thing I want to clear up is that x's and y's, I don't want to have to deal with both of them. So let's find a way to represent them in terms of each other. And that's where our function is going to come back for a second here. So I know that f of x is the square root of x. So like I could calculate things like f prime of x. It's just a derivative. So if I want to represent it as the 1/2 power, that's fine. So my derivative would be 1/2 times x to the negative 1/2, which I like to write as 1 over 2 root x. But like, why did I calculate that? Because like, what is the derivative? Well, the derivative we know in words is pretty easy. If I make a tiny change to the input, I make a tiny change to x, what is the resulting tiny change to y? And just in different notation, I could say if I made a tiny change to x, what is the resulting change in y? So we're connecting the idea that the derivative is just the slope at any given point. So with that, I can solve for delta y. So just algebraically multiplying both sides by delta x. That is another way of writing delta y. So I'm going to take this and just rewrite it all in the same variable. So the hypotenuse would equal delta x squared. But instead of delta y, I'm going to write delta x f prime of x, and I'm going to square that, because that's the same thing as delta y, so delta y squared. And then we have our square root. Now what I notice, and here I like to write it out just so I can see it a little bit better, if I squared that term, it would be delta x squared times f prime of x squared. So I am going to rewrite it like that just so we can see my next stage of factoring. Because I can see that both of these terms have a delta x squared in common. So I can just factor that out. oops, excuse me, that's a times. So this term would be a 1, and this term would just be f prime of x squared. And all of that's still under the square root. And then by our property of square roots, right, we can use the product property of square roots and break those into 2 smaller roots. And I know this is nice, right? The square root of delta x squared is just delta x. And then I have this square root, 1 plus f prime of x squared. Now, like, why do I care about that? Well, what we said was this was just one little slice of that curve. And that one little slice, again, if I look at it, was pretty straight. So this approximation is great. Now, what would make that approximation even better? Well, the closer I get, the more of a straight line it is. And the more of a straight line it is, the more accurate I could be. So if I look at smaller and smaller segments of this line, of this curve, they're going to get straighter and straighter and straighter and straighter. So as we were saying before, our calculus idea comes with, well, if I summed up all of those little pieces, well, what are all those little pieces, all those little hypotenuses? Well, we found all those little hypotenuses by taking some change of x and multiplying it by this other representation. But again, this is where calculus comes in. How small do I have to get? Or in this case, as I've been showing you with my graph, how zoomed in do I need to get? What does that little teeny change in x need to be? Like if I started like up here, I started at 0, and I changed x by 1, and that was way too big because that straight line didn't make a good approximation of this curve. So how small, how zoomed in do I need to get to make sure that my line is the best estimate? Well, calculus would say until that is 0, right? To get the most accurate, just like we saw up top here, I would want this to essentially be 0. Just like we were saying up here, when I'm splitting these rectangles, I want that width to come to be 0. Well, if I could partition this one curve into an infinite number of teeny straight lines, the little changes between them would be 0. So the little changes, summing all those little changes, and if those changes were going to be closer and closer to 0, that's where our integral comes in. So these two things together will make an integral, and we're summing up all those little changes in x, so that's where our dx comes in. Now, in this case, we start at the x value of 0, and we want an infinite number of partitions. So dx is going to cover as many as we can from 0 all the way up into the last x value of 1. So the only thing that was left in this formula was the square root of 1 plus f prime of x squared. So this formula here will give us the distance of the square root of x, the length of the curve, the square root of x, from 0 to 1. So let's go do it. Now, what I want to note with this is that the distance, setting up the integral is really easy. So like we already calculated the derivative, f prime of x, which I'm just going to show here again. F prime of x was 1 over 2 root x. So if I squared that, I would just get 1 over 4x. So in that in the function, I'm going to replace it like that. 1 plus 1 over 4x. dx from 0 to 1. Now, just as a note, a lot of times when we use this method, we can't actually calculate the integrals by hand. We need to do this numerically, meaning looking at a table, looking at what it approaches, or just using our calculator. So that's what I'm going to do right now on my calculator. I'm just going to type it in, and I urge you to do the same. So from 0 to 1, the distance between, the integral of 1 plus 1 divided by 4x in regards to x. And on my calculator, that gives me the number once it comes up here. It's going to take a moment. And I get 1.478. And if we go back to our original guess, right, the square root of 2, that's about 1.41, and we knew that it was going to be a little bit bigger than 1.41. We just didn't know how much. We got 1.47, so I think that's a pretty reasonable estimate. To start with 1.41, we can see that our answer is probably confirmed. Now that in general is always going to work. That argument that we did with the square root of x is going to work for any curve. So just to demonstrate that, if I just pick a random curve, instead of x the square root of x from 0 to 1. Let's just change that to like x to the third power. But again, if I find that curve on that interval, sorry, I got to zoom back out. Anywhere I look at that curve, if I zoom in again, still a straight line. So our argument of a bunch of teeny straight lines being added together to make a curve will hold for any function. So in general, that's our generalization, is that the length of a curve is always going to be given by the integral from a to b of 1 plus the derivative squared, square root of that in respects to dx. And if it makes it a little easier to see, we're squaring the derivative. So that's your formula for the length of a curve, or arc length, as our textbook or other textbooks might call it. An arc and a curve are really interchangeable at sometimes. So that's the arc length. What I'd also encourage you to see really, really, really quickly is like this general equation here, which I'm going to copy and paste. If I can. This equation here, we had a problem. We had to rewrite it because we were using x's and y's, and they were in different input values. One was in terms of x, and one was in terms of y. So we had to rewrite to get common inputs, per se. Because again, what I was going to do on my graph was I was making a change to x. Like we saw, I wanted to make a change to x. So I wanted to explicitly know how that would be affected. But the only reason we had to rewrite these because we were in different variables. So just to like kind of connect, motion is easy in polar coordinates. So we kind of set up the same idea here. If I had this curve, and some random point on the curve can be estimated by a straight line. So whatever I started there to there was some change in x, and there was some change in y. But in polar, we know that x is defined by some trig function. I'm not going to write that out loud. We know that x and y are just defined by some trig function, like, I guess I will. So maybe like x is the cosine of t, and y is the sine of t. So here, they already share a common input. So if I was going to look for the change in x, well, I know the change in x in polars is just dx dt. I know the change in y in polar coordinates is just dy dt. So I can make that direct substitution right away. And I can see that in polar coordinates, they're already in respect to the same variable. So then in polar coordinates, this is going to be the length of our hypotenuse, which we've seen before as some ideas of speed and some other things with polar coordinates. But that's the length of our hypotenuse because they're already in terms of t, so it's really easy. So I just need to integrate to get the length of the arc. So this is in polar coordinates, which again is usually simplified because they're already in terms of a common variable t.